able to fold a little tetrahedron. Right, you have 4 equilateral triangles. And so this is a puzzle for you when you're taking a break. And I'm only throwing this out at the beginning so that I can talk about it again later. So the question is, why do you get an equilateral triangle? The second question is it an equilateral triangle? And now I'm going to give you a sketch. So that's just the warm-up.
Yeah, then you would take them apart and you would just use it as a...
All I really wanted equilateral triangles.
Well, and that's a fun thing to be able to do, is make equilateral triangles. Especially if you like to make little models with your kids. Then it's nice to have a strip of equilateral triangles. You can fold them into tetrahedra, you can assemble the tetrahedra, you can fold them into octahedra. In fact, Martin Gardner has an article called, I think it's called Pleating Platonic Solids. Have you ever seen this article?
I'll see if it's on my computer.
It is on the CD.
Yeah, I have the CD on my computer.
Is that the CD
Of most of Martin Gardner's books.
Really?
There's like a CD of like 10 books or
Yeah.
something.
How do you, is it
I think it's distributed by the MBA. I also have it.
Yeah, I don't remember paying money for it. I'm not sure, maybe I did, but suddenly I got this CD.
Okay, so I would like to start today by talking about the division algorithm. So the division algorithm, you might remember, is when you take a number, an integer, you divide, well, it actually could be any 2 numbers. You divide one number by another, and you get a quotient plus a remainder. Here is one way of looking at the division algorithm. Well, so far this is not an algorithm. I'm just writing down one step. So this is the quotient. And this is the remainder. And of course, I could just multiply both sides by b, and I get another version of the same equation. A equals q times b plus r. And now here's the quotient, and here's the remainder. Okay, and we do this lots. Let's pick 2 numbers. What's your favorite integer?
It's 7.
7. Anyone else have a favorite integer? 7's a very popular one.
Kind of feeling 17 today.
17.
Yeah.
So 17 over 7. 7 goes into 17 2 times with a remainder of 3. And then what's the other way of writing this? 17 is 2 times 7 plus 3. There are the equivalent ways of writing the division algorithm. Okay, but what I'm really interested in is what happens to the left of the decimal point. Okay, so what does that even mean? Well, 17 is what in terms of place value? 1 10 and 7 ones. What would 0.17 be? Yep, this is now the 10th space, and this is the 1/100th space. Okay, so I know a lot of people know the division algorithm to the right of the decimal point, but it's really good to walk through it. I like to make it into a conversation. Let's just do 1/7. Very common one. 1/7. So you ask yourself, does 7 go into 1? No, it goes in 0 times, with a remainder of
1.
with a remainder of 1. Now I'm going to consider that 1 to be 10 tenths. Here's how I write down the division algorithm. I will write the remainder there, above the tenth spot. Now does 7 go into 10? Yes, how many times? 1 time with a remainder of 3. Now that's really 3 tenths. 7 won't go into 3 tenths anymore. So I think of the 3 tenths as 30 1/100ths. And I write the 30 there. Does 7 go into 30? 4 times with a remainder of 2, that's 2 1/100ths. Or 20 1,000ths. Does 7 go into 20? Twice with a remainder of 6. Now that's really 6 1,000ths. You know what I'd like to do? I'd like to stop right here. Actually, I should have stopped back here, make it a little easier. Remind me what happened here?
7 went into 34 times.
7 went into 34 times with a remainder of
2.
So if I were to stop right here, and the remainder is 2 1/100ths, how would I write that down? I would like to verify that this works and that we're really using the division algorithm here. So this should be an equation. 1/7 equals 1 100th plus, I'm sorry, 1/10 plus 4 100ths plus, now how does the remainder play out here?
2 700ths.
You know, I erased my general thing. Yes, it would be 2 100ths over 7. 2 100ths over 7. Can we verify that? Is that right? Obviously, this is going to be a 2 over 700. What's this going to be if I make it over 700? 28 over 700. And this? 70. And they add up to 98 100 over 700. And I was hoping we would get a 7th.
Oh, man.
I know. It's close.
It is close.
Okay, so that's the division algorithm. If we stop at any point, we can identify our remainder and get an exact equation. But, yes?
I'm sorry, what is 70? Sorry, seriously.
Okay, so this equation, 1/7 is 1/10
Yeah,
plus
yeah.
4 100ths and a remainder of 2 100ths.
Yes.
So that's what I wrote down here.
Yes.
Now the only peculiar thing is how the
Right.
remainder is.
Yeah. I'm okay with that.
Okay, so now I just put, I turned this into 2 over 700,
Right. Yeah.
and I gave everything else a denominator of 700.
Oh, you got a common denominator.
Common
I thought you were multiplying both sides of this. Oh, okay.
No.
Okay. Yeah. Gotcha.
Right. Another way of verifying would be to multiply both sides and turn it into the other form of the division algorithm. Okay, so now let's keep going with our algorithm. Instead of stopping and getting a remainder. So let's go back. 7 went into 1 0 times with a remainder of 1. That's really 10 tenths. 7 goes into 10 1 time with a remainder of 3 tenths. That's really 30 100ths. 7 goes into 30 4 times with a remainder of 2 100ths, which we just verified. 20 1,000ths. And let's keep going. And we were up to here. It goes in 2 times with a remainder of 6 1,000ths, which is 60 10,000ths. 7 goes into 60 8 times with a remainder of 4 10,000ths, which is 40 100,000ths. 7 goes into 40 5 times with a remainder of 5 100,000ths, which is 51 millionths. 7 goes into 50 7 times with a remainder of 1 1,000,000th, which is really 10 millionths. And now look, we have the same remainder. So if I kept going, what would happen? I would keep getting this pattern. And so shall we do it?
No.
Nope.
No need.
Convinced.
Convinced, okay. So this is probably a refresher. 1, 4, 2, 8, 5, 7, and we usually write a bar over that.
Funiculum, they call it. The funiculum.
Is the thing.
A funiculum is a sigil for repeated places.
Sigil?
I think a sigil is just a word that means it's a symbol for something, but I could be wrong. Okay, and another way to write this, suppose you have a long, long string of symbols that repeat. I've also seen this notation. 1, 4, 2, 8, 5, 7. Put a dot over the first one in the block and a dot in the last one in the block. And that way, if you have some repeating decimal where it's not a purely repeating thing, for example, x equals 0.1232323 ... I would write 0.1, and then 23 would be the repeating block. Or I would write 0.1, put a dot over the 2 and the dot over the 3, and it should, in this case, you wouldn't want to use the dots. Okay, so there is the division algorithm. Familiar? Yes.
Well, I've never seen this algorithm where you sort of use the remainder.
Yeah,
and
yeah.
then-
I just wanted to point out that it really is, that in terms of place value, you're really having this conversation. It doesn't go into 1. So we think of 1 as 10/10ths, and we report the answer in the 10th spot.
Right.
Now we have a remainder, which is in tenths. But it won't go in anymore. In fact, if it went in more, we would have had the wrong quotient.
So you're basically decomposing your units with that algorithm.
You are, yeah. Yeah, so, I mean, that is really exactly what is going on, is we're using the division algorithm at every step. We're getting a quotient and a remainder. What do you notice about the remainder all the time?
Less than the divisor?
The remainder has to be less than the 7. If it were equal to the 7, you'd get an extra 1 in the quotient. If it were bigger than the 7, you'd pick up more multiples of 7 in the quotient.
I think what I missed is just your explanation of why you decided to do that instead of drawing your house or your funiculum, doing regular long division.
What's the name for the division?
Well, the funiculum is this thing that goes
It's
on
the bar.
top. But
Yeah,
the
the
other
funiculum
part
is the
not a
bar.
name.
That's the word.
No,
but
when
there's
you
a
do
name
long
for the-
division, they
Oh,
also
okay.
call that.
7 goes into
Yeah, there's a name for
1.
that.
There's
That's not a name.
it
There's
is
a
though.
name
It's
for it.
two different
There are
parts.
parts of the-
Someone taught me that house is really the division line
This
and something that says we're going to continue, and that
Oh, that's interesting. I didn't know that.
it's really two parts.
Uh-huh.
But
And have you ever seen synthetic division, where you draw it like that?
Yeah.
I wonder what the motivation for that is. Well,
Synthetic line.
I think in South America they do it in sideways too. They have a slightly different algorithm, and they write it down sideways, which I never quite figured out.
my point is, so there's an algorithm here. There's just a step-by-step recipe for getting the decimal expansion of a fraction. What I want to get into right now is the conversation that produces those digits. And that conversation at every step is quotient, remainder, and place value. That is, here the remainder was at 3/10. But we'd have to stop if the remainder were just 3/10, so we make it 31/100ths and we report the answer in the hundredths space.
Just out of curiosity, how do your students receive this way of doing it? I mean, do your students like buy into it and say, wow, this is really helpful, I like this better? Or do they go, I'm going to go back to the house and then
No, they do fine with
Okay.
this.
What,
Alright.
what age do you teach it?
9 through 12.
Okay.
And I also work with 4th and 5th graders, but I haven't done this with.
Fine, thank you.
Yeah.
Appreciate it.
Now, let me think what, oh yeah, so the thing that I do with my geometry students when we do this is we talk about why the decimal has to repeat. Why must the decimal repeat? Yeah, that's the logic my ninth graders would use. But it's actually built into this.
Oh, because there's only so many digits that the remainder can be.
There's only so many possible remainders. And when do you know it'll start repeating?
Within 7, for this case.
As soon as you see a remainder that you saw before, the process will start repeating. So suppose you did something like 1 over 201. How many possible remainders? 200. There can't be 201 because then what? Cause you can't have to count out 0 as a remainder. That would be a terminating decimal. So you know that after 200 steps of this algorithm, suddenly you're going to have to see the same remainder. And then the process will start to repeat. Now, of course, usually, I mean, I wouldn't carry that at 200 steps. But you're guaranteed that at most 200 places it'll start to repeat. Now, and this is where the logic comes in. So now you know that when you divide an integer by another integer and expand it in decimal form, it has to repeat. So what did we just show? That A over B has a repeating decimal expansion. In other words, rational numbers, quotients of integers, have repeating decimal expansions. And students get the logic wrong all the time. Usually you can't show any, they say, why is square root of 2 irrational? And students like to say, because the decimal expansion never repeats. But that's twisted logic. We actually know that the decimal expansion never repeats because we can show independently that it's not a rational number, which there are some very nice ways to do without any algebra. So that's why I do it with my ninth graders. It's partly an exercise in logic while we review place value and facility with numbers. Yeah, and that drives me crazy. Why is square root of 2 irrational? Because the decimal expansion doesn't repeat. Well, how are you going to show that? How do you know that? They've got it backwards.
Can you show that?
Yeah,
proof
no.
to us?
Oh, sure. Okay, absolutely. I've run out of board space. I've just lost my eraser. Somebody moved it. Yeah, so let's take a 1, 1. Well, let's take a 45, 45, 90 triangle.
Okay.
Then the ratio of hypotenuse to side is root 2. So suppose that root 2 is rational. If root 2 equals, is rational, then we can put integers on the sides of this triangle. Okay. So that's an easy, there are integer sides here. So let's name M, N, and N. Now, suppose I do have integer sides there. There are lots of similar triangles. There will be one with the smallest set of integer sides. I could take out all the common factors. So there's a point of faith or discussion, at least. So I'm going to assume that there are no common factors here, that there is no similar triangle with smaller integer sides.
Ted, I'm sorry, I'm not sure where you got that statement.
Which?
If square root of 2 is rational, then the integer.
Because the ratio of hypotenuse to side is root 2. So this is another way of saying root 2 is m over n.
In its lowest terms.
So
In its lowest terms.
let's assume that we can express root 2 as a fraction.
Okay.
And that's what this statement is. If root 2 is rational. Okay, now let me erase this. And what am I going to do now?
Oh, so now you're doing n squared plus n squared equals n squared, and then using the mod to show that you can have common factors.
No, that would be an algebraic proof. I told you there was a nice
Oh,
proof
not
without
today.
any algebra.
Okay.
Okay, so here's the purely geometric proof. I'm going to take a compass and swing out an arc of a circle. And I'm going to put in a tangent here. And now let's do some geometry. So first of all, this is congruent to this.
Okay.
Why?
Because you made a tangent line to create a right angle.
They're both tangent to the circle from this point. And two tangents to a circle from a point are congruent. Okay, now everything else is really sweet. So first of all, this is an integer, correct? So this is an integer. So this is an integer. This is a right angle. Why?
Because it's tangent to the circle.
It's tangent. So what kind of right triangle is this? It's isosceles. That's a 45-degree angle. So that's an isosceles right triangle. So now I will mark this side with a tick.
Hold on, how do you know if that's isosceles? Oh, because it's 45 right around.
45, 90.
Yeah, okay.
But we just said that that was the smallest possible.
And he's already noticed. And now, what do we have?
We have a smaller.
This is an integer, so this is an integer, so this is an integer, but this was an integer. So finally, this is a new integer, and this was a new integer. So we got a smaller triangle. And you shouldn't be able to do it. If it is rational, then there should be a smallest triangle. Notice there's no algebra here. Kids are always confused by that algebra, right? Square root of 2 is m over n. You square things, then you do divisibility, and where did 4 come from?
Yeah.
But this is very visual. Plus, this extends. You could do this with a 30, 60, 90 triangle. Suppose you have integer sides here. You do the same thing. You get another 30, 60, 90 triangle, which has integer sides. And so that will show that root 3 can't be a quotient of two integers. But anyway, this is a little off track, but I love this argument.
Yeah, thank you, that's great.
Okay, next thing. Suppose we do have a repeating decimal. How can you identify what fraction generated it? So I just wrote one down, actually. X equals 0.1232323, da da da. So here's a trick. How long is the repeating block there? 2. So I will move the decimal place over 2 times. What do I multiply by to move the decimal place over 2 times? Okay,
But you gotta do it.
and so I multiply this by 100. And what do I get? 12.32323233. And notice what happens. After here, if I subtract, everything cancels out. And so look, I get 99x equals, what's 12.3 minus 0.1? 12.2, and so x equals 12.2 over 99, which is not a quotient of two integers. Easy to fix, multiply by 10. 122 over 99. And if you have a calculator, you can verify that. Or we could do the division algorithm. Shall we do the division?
Don't you mean 990?
I do. Didn't I write 990?
Oh yeah, you did.
Yeah, I did. Yeah, no.
Why didn't you just?
Multiply by 1,000.
Yeah.
Okay, let's multiply by 1,000. I think you will see there is not cancellation, complete cancellation after the decimal point. So what do we have?
Not multiply by 1,000. What is this?
0.1232323.
Wait.
If I multiply by 1,000, I get 123.232323.
You get the same if you
Oh, I
multiply
mean-
by 10.
Multiply by 10. And
It would be on
same-
cube.
Same deal. Yeah, so if you want to move the decimal place over the same block so that when you do the subtraction, the blocks match up and they cancel out completely.
What, okay, I like that, but why are you teaching your geometry students how to divide that way? That's what I
I teach them the division algorithm and how to turn rational numbers into decimals for two reasons. It reminds them about place value, and it gets them to the correct logic of if it's a rational number, then it has a repeating decimal expansion. Because in geometry we do a lot of logic. That is if-then state. They really have to understand
So you, okay.
if-then statements.
Nice.
Okay, now let me look at my notes here. Now, really what I wanted to do was a little base 2 today. I hope that's okay. So what does base 2 mean?
I don't understand base 2 and base 3 that well, because it's just so back there, and so I'm excited about this.
Binary code.
Maybe refreshing.
It is. So this number means a tenth plus 4 100ths plus 2 1,000ths, 8 10,000ths, and so on. What would this number mean in base 2? Now this is a ones place, this is a tens place, this is a hundreds place, and I still think of it that way, tens and hundreds, except 10 is now 2. And so this is going to be 1 for the ones place, no 2's, and 1 4. So this is the number 5 in base 2. Okay, so that's pretty simple. Now, there's a way of taking base. Let's pick a number. Did you have another favorite number?
27.
27 is a good one. Here's a way of turning 27 into base 2. I'm going to repeatedly divide by 2. So 27 divided by 2 is 13 with a remainder of 1. 13 divided by 2, 6 with a remainder of 1. 6 divided by 2, 3 with a remainder of 0. 3 divided by 2, 1 with a remainder of 1. 1 divided by 2, 0 with a remainder of 1.
Isn't this related to like the Russian peasant method of?
Actually, it is. The Russian peasant method, without saying so, turns numbers into base 2.
Right.
So, what's the deal here? 1 1 0 1 1. You know, 27. That's kind of unfortunate because it's a palindrome, so you can't tell that you're starting down here. 1 1 0 1 1. This is this one. Now, can we verify that?
Well, you can just add them up.
You just add them up. That's a 1. What's the next one?
2.
A 2. How many 4s?
0.
How many 8s? 1 8. How many 16s? I hope that adds up to 27.
Yeah. 2 makes 10 and then 17.
Now, what should happen if we multiply by 2? What happens to a decimal number when you multiply by 10?
Oh, you moved the decimal.
You move the decimal place over. So 54 should be, if I multiply this by 2, I should just move the decimal place over. 1 1 0 1 1 0. Question mark. Can you check to see if that's true? Because all I did was move the decimal place over. So take a moment and add up.
So you can just take what we did right above that and multiply each number by 2.
Okay, thinking like a mathematician. I don't really have to add them up, because why? He just said it perfectly. When we did it above, this one was a 1, and this one was a 2, and this one was an 8, and this one was a 16. But now that first one is a 2, and then a 4. So basically it's this addition, but instead of this being a 1, it's a 2. And instead of this being a 2, it's a 4, and instead of this being an 8, it's a 16, instead of this being a 16, it's a 32, but we don't have to add them up. We just multiplied everything by 2, so the answer has to be multiplied by 2. Okay, so yes, multiplying by 2 in base 2 just moves the decimal place over.
So can we do the same thing with the bases? What if we went to base 3?
Yeah,
You know,
it works base 3.
base-
Let's pick a number. I don't want to pick 27, because it's a power of 3. Let's do 24, okay? Do 24, divide by 3. I can do it. 24 over 3, 8 with a remainder of 0. 2 with a remainder of 2.
I'm sorry, that's second set. The first one I get. You write the 2, are you writing 8 by
I'm dividing by 3 now, repeatedly.
He's dividing the remaining.
Okay, so you're dividing 8 by 3, you're dividing the remainder. Okay,
Yeah.
gotcha, thank you.
And now I'm dividing 2 by 3, and I get 0 with a remainder of 2. And so 24 should be, starting from the bottom, 220 base 3. And now we have to understand the place value. This says there are no 1s. In fact, 24 is a multiple of 3. It has to be divisible by 3, so there can't be any 1s. How many 3s?
2.
2 3s, that's a 6. And what's the next place, base 3?
9.
A 9. And there are 2 9s, so that's an 18. They were supposed to add up to 24. Now, there's another way of turning a base 2 or base 3 number into its decimal form. And how many of you have heard of Horner's method with evaluating
Before we
polynomials?
go backwards,
Yeah.
what happens if you do something like base 16? I mean, like we do
Exactly the
opposite.
same method. Let's pick a bigger number now. How about,
Let's do
16
decimal.
squared is already 256. So, shall we pick a big number? I'm going to need help.
Well, how about
987. Divided by 16, anyone?
Wait.
6 with a remainder of, because 6 would give you 96. Oh no, 7. No?
8.
6.
remainder is 2.
Thank you.
15 times 6 is 9.
6 times 16, no, 60 will be 980, so it'll be 61. That should be 986. Am I doing this wrong? Can somebody?
Yeah, it's 61.
61 with a remainder of 1, I believe.
11. Remainder 11?
Remainder of less.
Remainder of, let me think.
That's 11.
Thank you. Remainder of 11. 16 goes into 61 how many times? It goes into 64 4 times, so it'll be 3 with a remainder of
15.
48 to 61, 13. 16 goes into 3 how many times? 0, I can do this one. 0 with a remainder of 3. So, in base 16, I have a 3, a 13, and an 11. There are 11 1s, there are 13 16s, and there are 3 16 squareds.
That should be 16, right? In the
Should
font.
be 16 is the base, right?
Okay, I repeat, I wrote 16 the second time.
So 3DD.
Yes, and so, right, in base 16, they actually invented letters to go in the places after 10. But I find it really helpful with students to put the places in and actually put numbers in there. Because, I mean, suppose you multiply, I don't know. There are lots of answers to multiplication problems that are really, it's legitimate to say, you have an 11 in the 10 space. It's 100 plus 11 plus 3.
So, it seemed like a lot of people, myself included, were tempted when we got the 61 to say, oh yeah, it goes in 4 times. So why not just put a 4 and then a remainder of -3, because that's easier to compute.
I think that would work, actually. And then when you get down to this, shall we try that? I'm a little hesitant. When you get down to this step, it would be like saying I have a remainder of 17 here. When I get down to this step and I want to turn it into the usual way of reporting a number, I'd have to turn the 17 into a 1 with a 1 here. So you could do the same thing with a remainder of -3. Shall we see? Okay, fingers crossed. 987, so 64 with a remainder of -3. 16 goes into 64 4 times with a remainder of 0. And 16 goes into 4 0 times with a remainder of 4. So, I think...
No, actually, the 64 came when at the neck where you did the 3
61.
instead of the 3.
Oh.
Yeah.
Okay. Sorry.
Yeah, because
So, 61 with a remainder of 11.
yeah, because that one was too
4
hard to
with a
do.
remainder of -3.
Right, that was the one that felt
And-
satisfying.
0 with a remainder of 4.
Mm-hmm.
So, 987 equals 4 16 squareds, -3 16s, and 11 1s. Now, how can we turn that into a legitimately reported number?
You would borrow the one from,
Borrow 1 from here,
which is actually.
which is
16,
really 16. 16 minus 3
13.
is 13, so it's actually going to work. When we borrow the 1 from here, that turns into a 3. 16 minus 3 is 13. We don't have to touch the 1s.
Can you go over a quick proof of why this algorithm works? Is that
You know, instead of proving why it works, let me show you how to turn it around. Okay, so let me take this number, 3, 13, 11. I will write my 16 here. And now here's Horner's method. Drop the 3 down here and multiply 16 by 3. And I get 48. I'm going to need somebody with a calculator. Add 13 to 48.
61?
Multiply 16 by 61. 976?
I have a calculator.
Well, I knew that if it were, you know... Now, add the 11, and I get 987. So, what did I just do? What got multiplied by 16 2 times? The 3 got multiplied by 16 once, and then it carries along. Shall we write this out?
Okay, yeah, no, I get that.
With all of the nested...
Sure.
So what do I really have here?
Cool.
16 times 3, I'll put a plus 0, just, okay, plus 13 plus that times 16, and 11 plus that times 16. So what did we just do? The 3 got multiplied by 16 3 times. The 13 got multiplied by 16 twice. And the 11 got multiplied by 16 once. And that's exactly what we mean by those digits base 16. Now when you teach this with so-called Horner's method, which is usually done with polynomials, which is why it's so important to stress place value whenever you do these things, you actually get a division algorithm, and the division algorithm shows you that you're really evaluating the polynomial when you do this. It's called synthetic division.
You multiply by 16 one time tonight, didn't you?
Did I?
Yes. It's 3 times
You're
16
right.
squared.
You're right.
And yeah.
There. I've added the 11 at the end.
Right.
3 got multiplied by 16 2 times. 13 got multiplied by 16 once. Now, if you analyze this, you'll see that this method is just the backwards of that. Okay. So now what I really wanted to talk about was what happens after the decimal point. So let's see, can we go back to base 2? And then you can always ask me later what happens in base 16. Let's do base 2. I would like to expand 3, or 1/3, base 2. And so you have to remember the whole conversation that we had when we did the division algorithm base 10. It's actually really simple. Does 3 go into 1? No. It goes in 0 times, and the remainder is 1. And so I'm going to report that 1 as 2 halves. Does 3 go into 2? No. 0 times with a remainder of, it's still the 1, which I'm now thinking of as 2 halves, which is really 4/4. Does 3 go into 4?
Yes.
Yay! 1 time with a remainder of 1/4, which is 2/8. Does 3 go into 2? 0 times with a remainder of 2/8, which is to say 4/16. 3 goes into 4. 1 time with a remainder of 1/16, which is to say 2/32.
0 again.
And can you see what's happening? It's going to be repeating 0, 1, 0, 1. So 1/3 is 0.01 repeating base 2. Hold on, you say. That can't be right. Let's start with our little trick. Here's 0.01, 01, 01, 01, 01, doo-doo-doo. Base 2. What do I multiply by to move the decimal place over? 2. How big is the repeating block? I want to move the decimal place over 2 times. I will multiply by 4. 4x will be 1.01010101. Subtract. What cancels out? Everything after the decimal point. 4x minus x is 3x, and all I'm left with is 1. Whatever number that is, it's a solution of 3x equals 1. It's a third. Okay. So we did it 2 ways. We did the division algorithm, base 2, and we verified using our little trick for turning repeating decimals. By the way, these shouldn't be called decimals. Nobody's given me a good name yet. Decimals, somebody told me they should be called. Because it's 2. But then you'd have to come up with a different name for every base, so you might as well call them decimals. Now, I'm going to give you some strips of paper here.
What do you call the decimal point? Isn't there a Latin word for that?
Here's our resident expert.
Right, like, there is.
Yeah,
There
that's
is.
what you get for opening your mouth.
So then,
Okay, I'm giving you strips of paper.
Are we, oh, you're giving me a whole bunch of strips.
A whole bunch, just because why not? And here is what I would like you to do. I want you to take the strip of paper and fold so that you're putting a crease at the 1/3 mark, but don't be too careful, okay? And in fact, don't crease it all the way down, just give it a little pinch near the top edge so that you can see where your pinch is.
What do you mean by the 1/3 mark?
Yeah, see, how do you find the 1/3 mark?
You said don't be too
I
I
don't
said
agree
don't
with
be
your
too
estimate.
accurate.
Okay.
You could even fold it to the 1/2 mark. Now, open it out. Do you see where your pinch was?
Yeah.
Fold the other end in, so the end goes right to the pinch, and give that a little crease. Again, don't crease top to bottom, just give it a little pinch near the top edge so you can see where that mark is. Open it out. Do you see your latest mark? Fold the first end into your new crease. So you're just going to go back and forth, left, right, folding the end into your newest pocket, your newest crease.
Wait,
Isn't that kind of where I am?
yeah, isn't that originally?
Oh, you know, if you
You did it
if you pinched well at the
This is why
one-third
you want
mark,
us to be inaccurate.
Right.
Oh, okay.
Oh.
Better start over.
and
'Cause mine's awesome.
I did this
Yeah,
once.
Because I sort of, that's how I pinched it
Mine's-
first.
I had someone once say, you know, I'm a seamstress, so I just folded at the 1/3 mark with my first
That's
fold.
what I
Yeah.
was thinking.
I said, well, I don't think that's going to help you when we do a fifths.
Ah,
Okay, and keep going back and forth. And you'll find the pinches stop moving after just a few sequences. And then, of course, once your pinches stop moving, then go ahead and pinch all the way from top to bottom, so you're not just marking the crease, but you have now folded perfect thirds. Or are they? Are they perfect thirds?
más o menos.
So paper folders have ways of folding perfect thirds. That is, a geometric construction that gives you thirds. But of course there's error in any way you do anything. Here there's error, but you're actually reducing the error at every step of your method. So this method will give you is as good as the perfect way, even though it's really not perfect. What's going on here? So let's draw a strip of paper. So here's the way I explain this when I do this with little kids. Here's our first crease. Okay? We are guessing that that's the thirds mark. So I will report this as a third plus or minus some error.
Would you keep cutting the error in half, I suppose?
Which makes this what? Yes.
Makes it 2/3 plus or minus. Yeah.
2/3
Minus
plus or minus the error. You're right, it should be minus plus. So what happens now when I fold this edge in here? When I fold this edge over to here, I fold this in half. And this is now what?
1/3 plus or minus the error.
1/3 plus or minus half the error. And then notice we're in exactly the same position we started with. We have a crease at what we guess to be the thirds mark. So let me erase all this then. There's 1/3 plus or minus half the error. What's this?
2/3 minus plus the.
2/3 minus
the
plus,
error.
I love that. Half the error. So when I fold in the middle there, a new crease, better in the middle, what will this be?
1/3 plus or minus even 4.
1/3 plus or minus a quarter the error.
So it's like bisection.
So whoever said the error gets divided by 2 at every step was nailed it. The error gets divided by, so if you go left and then right, your error is now a quarter of what it was. Every time you do both edges, you're multiplying the error by
You're
a
going to show us
quarter.
how to do 1/5?
Let's do a fifth.
Yeah.
But before we do a fifth, we have to figure out what sequence of folds is going to give us the fifth. So, what's
Well,
really...
that thing is called a radix point or a radix point.
Ah, the radix.
The
So,
what is?
the
divisor?
decimal point.
Oh, the decimal point,
is
radix.
the-
In Latin.
Yeah, radix point, or I don't know if it's radix or radix.
How do you spell it?
Probably radix.
R-A-D-I-X.
Okay, so let's
That's good.
let me pick a point here and call this x. X is a fraction. It's a number between 0 and 1. Here's 0, here's 1.
Can I make a guess at so where we're going with this?
Yeah?
Alright, so if we have like 5 sections, we're going to have 4 folds. Are we kind of going to play this game with 4 I don't know. I picture making 4 folds and then trying to make the 4 folds, the creases.
Yes,
Work
you're
not
making
gonna-
4 folds.
I don't know. I don't think I'm trying to like anticipate where am I going.
But-
I'm talking the creases rather
But
than the end points.
when you
I
fold
think that's-
sevenths, there are 3 folds.
That's gonna be like so.
So, but we're going to get there. So the pattern I think you were looking for isn't quite what you think.
Yeah.
Okay. So what happens if I fold the left end into my crease at x? I get a new crease at what point?
X over 2.
X over 2. What happens if I fold my right end in to my crease at x? I get a new crease where?
One minus
X
X
over
over 2.
X plus 1 over 2.
1 over, yeah.
1 minus
X,
x over
half.
2.
Yeah.
No,
So half
it's
minus
X plus 1 over 2.
Well, this length is 1 minus x.
Right.
So this length is 1 minus x over 2, but we're
Plus
starting at x.
You can also think of it as the average between those 2 locations.
Which is how, but this is
Right,
good.
that's great.
Wow.
Okay, so now do the algebra, what do you get?
1 plus x over.
1 plus x over 2, which is instructive. If you have 2 numbers, what's the number halfway between them?
Add them in.
The average. Add them and divide by 2. That's what we got. Here's x, here's 1. This is 1 plus x over 2. Now I'm going to think of that as a half plus x over 2. And I'm going to think of this as x over 2. Okay, now, I'm also going to think of this operation as folding from the left, and I'm going to think of this operation as folding from the right. So every time I get a new crease, I get a new x. So if I start with x, and I do the operation L, what's my new crease? X over 2. Now let's think in terms of base 2. X is just a number. I can think of it as base 2. Maybe I should think of it as point x. Now what does dividing by 2 do, base 2?
What's the decimal point?
Moves the decimal place over. So now my new crease is at 0.0x. Now I'm going to do my operation R. What does R do? It moves the decimal place over. Then it adds a half. What is adding a half base 2?
You put a 1 just to the right of the decimal point.
It adds a 1 to the right of the decimal. So first we move the decimal place over. That puts a 0 to the right of the decimal. And then I insert a 1 in that spot. So this is going to give me 0.10x. Let's keep going. Do the operation L.
0.010x.
0.010x. Do the operation R. 0.1010x. Now, what did we say the decimal expansion for a third was? 0.0101001. So all I have to do now is do L again, and I have 0.01010x. Notice x makes less and less of a difference. The initial guess you make doesn't matter. We are converging on the decimal expansion 0.010100101, which is a third.
That's awesome. Very cool.
Okay, so maybe we can figure out what decimal. So suppose I gave you the decimal expansion. Who wrote 2 ones there?
The gnome.
The gnome. Suppose I gave you the decimal expansion and asked you to turn that back into a sequence of folds.
Just subtract from that one.
The O's will be L's, and the R's will be 1s.
What was the question again?
Suppose I gave you a decimal expansion, and I said, let's turn that into a sequence of folds. Because here I gave you a sequence of folds, and we quickly figured out what's the convergent crease. Where do we end up? So now I want to go the other way. So,
So if you had like a 0.111111, that would just be doing the right fold, the right fold, the right fold, the
Yeah.
right fold over and over.
in fact, what is, this is, you know, I haven't pointed to this sheet at all. What is 0.111111 base 2?
Oh, based.
Half?
You're absolutely right. It's a half plus a fourth plus an eighth plus a 16th.
Which is 1.
Which is, 1/2 over,
Look at the first picture on the page.
It's not 1.
no, it's,
Yeah, but
it's,
1/2 over 1 minus 1/2.
It's not a third. A third is 0.01.
2/3.
It's not 2/3.
Once. It is one.
It is 1.
1/2.
There's a really nifty
But
picture.
it's base
There's a
2.
really nifty picture right there.
oh,
In fact, take
Yeah,
that
it's
square.
that.
That
Okay,
square
yeah.
has area 1.
So you round it up to base 2, yeah.
And I've broken the square up into a half on the left, and then a quarter in the lower right, and then an eighth, and then a 16th, and so on, and it comes down to 1.
But
Let's do it. X equals 0.11111 dot dot dot, base 2. What do I multiply by to move the decimal place? So, oh, I should ask you though. We should have the whole conversation. How long is the repeating block?
1.
1. How many places do I want to move the decimal place over? What do I do to move it over? Multiply by 2. So 2x, what happens after I multiply by 2? I get 1 plus 0.11111, which is x.
And then you subtract that, and you get 2x equals 1.
2x equals 1? Yep.
And x has to be a...
No, we don't get 2x equals 1.
Oh, yeah,
You get X equals.
We get x equals 1.
Right.
You know, this is no different from what our students get so confused about, which is why is 0.9999 base 10 equal to 1?
Yeah.
But no, my question was, in the left, right sequence of folds,
Yeah.
we're doing some kind of correction where the x doesn't matter anymore.
Well, the x is still there, it just gets pushed
Right.
farther and
But
farther
if
out.
you have a 0.11111, which signifies just a right fold and a right fold, and
Yeah.
I don't see it correcting itself.
Well, what is it converging to?
So you keep folding the paper no matter where you
If
start.
I keep folding
you
the
keep folding
paper
it, it's gonna end
to
up
this
just on top.
crease, no matter where I start, where is
Oh!
the crease
Right,
ultimately
okay,
ending
sure,
up?
sure,
That's
okay,
very cool.
got it.
Okay, now, this is actually instructive for students. Why is 0.999999 never ending equal to 1? They get really messed up about this. How can you, but they shouldn't. 2/6 is a third. We're totally used to being able to write numbers in multiple ways that represent the same number. So why should we be surprised that there are 2 ways of writing 1 as a decimal? So here's the conversation I have with my students. What's the difference between 1 and 0.999, and it terminates? How close is that to 1?
Close.
The difference is exactly a 1 in that last spot.
Wherever you're ending it.
And if that, so suppose I push that last spot out further. What's the difference now? 0.000001. Suppose I push that distance out further. The zeros go on further and further. If I never let that 1 rest, I just get the difference is 0. They're the same number. The difference between that number and 1 is 0. When is the difference between 2 numbers 0? I know, it's a trick question.
But you're not really surprised that your students are puzzled by this, right?
No, I'm not.
Because I've been told by that.
Yeah.
What's wrong with you people?
And actually, I have a slight bone to pick with my own trick here of multiplying and moving over the decimal. I don't want to roil the waters and show you why that bothers me. We shouldn't just let ourselves do anything and pretend it gives us, well, I will, I'll show you. suppose I start here at the right, and I have point 9999 coming into the right, point 0, and I call this x. Okay, what's the length of the repeating block? 1. So I want to move the decimal place over 1.
No.
No.
Actually, I'm going to divide by 10. Okay, so I get 1/10. And what am I going to end up with this number? 0.9999. 9.9. There we go. And now I'll subtract. X minus 1/10 x is 9/10 x. Everything to the left of the decimal point goes away here. And what am I left with? 0 minus 0.9.
0.1.
Oh,
wait,
Negative.
0.9.
Negative 1/10.
Yeah.
I end up here with x equals negative 1/9.
Well, that's what happens when you get your definitions mixed up.
No,
So-
it's that,
Because this
the
is
method
not a
is
repeating.
completely different than that method.
Yeah.
Because over
Actually,
there,
no.
what you're doing is you're subtracting off the
You added a whole
infinitely
place
where the
up.
last
All I'm doing
place-
is I'm canceling out everything to the left of the decimal
But
But
point.
it's like an
No.
order of
Yeah,
magnitude bigger,
You're
right?
making my head hurt.
The problem
Stop.
is
Okay, I told you I didn't want to roil the
You're breaking
waters.
so many rules.
That's
But-
like, it's like 10 times infinity, and you're subtracting
It's
10
true.
times infinity.
This number
minus
is infinity. And when I manipulate it, I get an answer. Actually, this answer kind of makes sense. What happened when I divided by 10? I didn't make it smaller.
It's an order of magnitude less.
No, it got bigger.
Oh, that's.
I got the same number back plus 0.9.
That's
I
right.
divided by 10, I got a bigger number.
That's funny.
So should we be surprised that our answer is negative? What kind of numbers can you divide by 10 and get a bigger number? Negative numbers. So there's at
And
least
infinite numbers.
and infinite numbers. There's at least some consistency here in our wrongness. Okay? But I just want to say that this is exactly the same method. We're making an assumption at the outset that it's okay to manipulate this thing as if it were a number.
Right, so in other words, there we see it's wrong because it's clearly an infinite number. Whereas here, it could be wrong because it's an infinite object
Yeah.
that we think is a finite number,
But we
but
think
it's
it's a
still,
finite
it's not a normal number because it has infinitely many things in it.
Yeah.
Well, I would just like to argue that, I see, so you changed the left and right direction of our definition of repeating. Because I mean, I would argue that that is not one digit repeating because it ended at 0
Oh, but I was looking at it going
But
to
you're
the left.
Repeating to the
flipping it.
left.
to the other
Still a
side.
repeating decimal. It's just the way no one would think of to do it, because
Yeah.
that's crazy. And I'll totally cop to that. Okay, so let's get back to base 2. I'm going to give you an exercise now, because now you know how to do the division algorithm base 2. What is 1/5 base 2? So you have to have this whole conversation now. Does 5 go into 1?
Oh, sorry, we're in phase 2?
Base 2.
Okay, I was talking about.
Base 10, yeah, we're done.
We're doing 1/5 in base.
1/5 in base 2. So does 5 go into 1? No. 0 times with a remainder of 1. Which we would think of as 2 halves. So we write a 2 in the halves spot. And a 2 above the halves spot. Does 5 go into 2? And that's really 2 halves, which is our answer. The answer is no, 5 doesn't go into 2. So we multiply it by, so it's a 0, with a remainder of 2 halves, which we think of as 4 fourths.
So 4 goes here?
Yeah. Now does 5 go into 4? And so that's 0 times with a remainder of 4 fourths, which is to say how many eighths? 8 eighths, and that's still our 1. So put the 8 up there. When does 5 go into 8? 1 time with a remainder of 3 eighths, which is to say 6 16ths. Does 5 go into 6? And you're off.
Just if you just kind of.
Did you get
Each place is
a decimal?
twice as many if you move over one. So just keep multiplying your remainder.
It should be repeating.
As you go over. Don't think about where you are. So like you just do 6 divided by 5 is 1 with 1 remainder, but just multiply by 2. Let's take that. No, so, 6 divided by 5 is 1. So that's correct. And you have that remainder of 1, which then you're gonna, when you move it to the spot, that 1 pops into the 2. Like if you had a remainder of 7 and you went over 1, it would become
No. And so the remainder is 1.
the
which is
remainder
2
always
halves.
doubles when you go to the
Right.
It goes 0 times. So 2 halves, which is 3
4,
fourths.
4,
But now it'll go into 8.
right. So the 1 goes here. All right.
And where's your decimal point? You should put it between the first two.
Between the first, right there?
Yeah.
Okay. All right.
And now it goes in 8 with a remainder of
3.
3.
So
And of course that's 3 eighths, which is to say, how many
6
16ths?
16.
6
So I
16ths.
knew that went in there 1.
So
So it's 0, 1, 1 repeated.
1, and that's 1 over 2, there's 2. And that's 0 there.
And that'll be 0. Because your remainder's back to 1.
Well, I like them. I don't.
Okay, shall we do this together
It should go in the logs.
and see what you got? So here's the conversation. Does 5 go into 1? It goes in 0 times with a remainder of 1, which is to say 2 halves. Does 5 go into 2? 0 times with a remainder of 2, that's really 2 halves, which is to say 4 fourths. Notice that's still our 1. We're now reporting it as 4 fourths, but it's still that 1 that we couldn't divide into yet.
Right.
Does 5 go into 4? No, it doesn't. So that's 0 times with a remainder of 4 fourths, which is to say 8 eighths. Does 5 go into 8? 1 time with a remainder of 3 eighths, which is 6 16ths.
Get 1.
And it goes in 1 time with a remainder of 1 16th, which is 2 32nds, and we already saw a remainder of 2. So if you keep going now, we should get 1/5 equals 0.01, oops, 0011, 0011, 0011, dot, 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 base 2. Now, would you like to verify that using the trick? X equals 0.001100110011, dot, 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 base 2. What's the length of the repeating block? 4.
Okay, so we're gonna multiply by 16.
So we're going to have to multiply by 16 to move the decimal place over
4 places.
4 places. And what am I going to get here? 11.0011, 0011, 0011, da, da, da. I'll do the left-hand side. 16x minus x. And what do we get on the right?
11.
11.
It's 11 base 2. 1 base 2. What is 1 base 2?
That's 3.
So I get 15x equals 3.
X is equal.
Oh, and I meant, we got 3
3
15ths.
over 15, and that's 1.
And that's 1/5.
Pretty good.
Okay, so
Alright, that was wild switching bases like that.
it is wild switching bases like that. It really makes you think about what that place value means. Now let's go back to this strip of paper, which I know everybody has more paper. What sequence of folds will you do to get this number? Here's my initial guess. Now there's a weird thing about this sequence of folds. I claim the sequence of folds is going to be RR, LL. Here are the two R's and the two L's. And then two more R's, RR, LL. And two more R's. And two more L's. Because after I do this sequence of folds, I will have pushed out the X. But don't take my word for it. Pick a spot and fold twice from the right, twice from the left, twice from the right, twice from the left. You were already done?
Yeah.
Wow. Did you get fifths?
Yeah, because
Now remember, grab a strip of paper for me. You're always folding the edge into the new pocket you made. So I make my initial crease. I fold this into that pocket.
This is for increasing originally thirds.
No,
At
the initial crease just goes
fifths.
anywhere.
I'm trying to fold, but it doesn't matter what your original
Yeah, so I'm
crease
just,
is.
I'm saying that the fifth, right?
And then when I open it up, I will fold this again from the left to that pocket. Here's my new pocket, and I fold the other side into that pocket.
So you fold it all the way back to that other,
Yeah. Every time you fold the edge to your last crease, your most recent crease. Is it working?
I had to figure out if I did one or two rights just
Well, you should be able to look at where your most recent crease is. That's about the fifth mark.
two folds are both going into the most recent crease.
Yep, so here's one fold into the most recent crease. I open it up and I do that into that crease. Open it up, now I'm going to repeat from the other side. This goes into that crease. I open it up and I go into. And you'll find very quickly the creases stop changing.
When you follow, you go from left to right with the algorithm, or you go right to left?
Well, it's a funny thing about reading the algorithm. We read the decimal place from left to right. But the sequence of folds, we're going to read from right to left. But, you know, it really doesn't matter. You're either going to end up with a crease at the 4/5 mark or at the 1/5 mark.
Now, is this done in the real world? Like
I use it to fold my bills in thirds when I put them in my drawer.
so that's the real world.
You fold and fold and fold and fold, and you just have a curve and crease.
Well, you know,
Yeah.
actually in origami they have a method which is just making an S and then
so you
adjusting
use,
it until
That's how
things
I
line up.
Yeah,
But,
so
but
you-
yeah,
you start
because
your
with a
first
bill,
guess, right,
you can
was
make your
first-
initial fold
first
pretty
guess
good,
was
and then I
this.
make a pocket,
Yeah.
and I fold it in
And
the other way.
clearly
One
that-
repetition is good
Yeah.
enough to
Yeah,
go
which
in
is
my
good.
wallet.
So right, so there's your first one,
I'm not exactly following.
and that's
Oh, yeah,
an
here.
R, and
So
then
here's
you do
the
another R
Yeah.
there.
Okay,
So here's my initial guess.
yes,
Okay.
terrible guess, good job.
There, okay. So now
So
I
now
need to
do-
do two folds.
And now
No,
I'm
no,
gonna
not-
do
okay.
an L
Crease
starting
with
on
the
that
fu-
one.
That's
right there, like a little crease.
And I bet it will
Open it up.
already be
And fold
close.
the right edge into there.
Because of
Oh,
what you said,
okay,
we're,
so fold this one over here.
That's all.
when we were doing this thing, that you
Okay.
know, the error.
Now there's your new crease, open it up,
So now you gotta do picking the
fold
left.
this into there.
So if you put it market X,
Open it up, there's
And
your
now
new
I'm folding
crease.
it up.
Fold the right.
Yeah, I'm pretty happy with my fold.
Let's try.
So I still think it's really
Okay.
wild that you multiply
No, I didn't,
Right.
I just didn't
Fold
try.
right.
a left
X,
value
one half
with
plus
base
X over 2.
10 and a right value.
So
It's
the-
all base
by
2.
base
basically the
2.
function of
Oh,
the left
you
fold
mean,
is
Yeah.
taking
you mean
X
here.
value.
Yeah.
yes, you know, you're right, that's worth
Oh,
mentioning.
right, and that's why it's the.
On the left-hand side, I have 15.
For,
In base 10.
Because
And you have to
basically
convert
what you're
before you
doing is
divide.
you're taking your
that's
value
because I
divided by
multiplied by
two.
2. I mean, I could have reported it as I'm multiplying by 2 to the 4th, which is 10,000
that you have options
base
to
2, but that's 16 base
make.
10.
And in base two.
So yeah, I didn't mention that
If you
when I
have
did
the
it.
number,
No, it's okay, I just did.
I multiplied by 2 4 times, and that's 16.
that again, you get 0, that's not 2 zeros.
So this was my most recent create.
And a one.
Coming back to this on the right.
Right, when you
I don't
add
know.
half, when you add half to a number, half in base
Isn't
two
it
is
back up?
right?
Yeah.
So if I add half to
Like
this,
I think somehow you're a little too small.
if I were to add half to this, then it would
Here,
be
let me
closer
do
to
it.
this.
So,
Yeah.
here's my initial crease.
And you take a number
So
of
I'm going to go from this side, pinch the crease,
Right.
If I took a
and
number
then
of
this
x
side,
or point x,
pinch the crease.
and
Open it up,
this, and
and
then this,
reverse.
and this,
from this
Well, how
side.
come you're not going to this person?
No, this is my most recent
and
crease,
then adding the one,
Okay,
isn't it?
and then divided by
I
two.
folded it into there.
adding the
Okay.
one,
There's my most
Right.
recent crease.
Okay.
the one,
I go in there,
and if I want to do this to it,
pinch,
a couple times,
there's my most recent crease.
so as you're going
There.
from this
There,
one,
and I come from the right.
from this, and then this, and then
okay, so now this is your most
Now
recent.
that's my most recent crease. If I wish to continue,
So
Right.
from here to here, what I did to
There.
the x was I did 1, 2, 3, 1, 2, 3.
here's my most
So
recent
it's the right folder.
there. And that should be about
Oh.
fifths.
Do you turn this into a fraction?
But that would be
The
a
back
whole
version, would
piece
that
on the
tell you what
regular.
that kind of
Okay.
is useful for?
I mean, I would take a whole piece of
Ted?
paper.
Yes.
Can you, I lost my
column.
that left, right,
Yeah.
and this part.
Okay, it's because, it's already gone.
Oh, yes,
So,
right, right, and you can do that
when
now.
you crease from the
Yeah,
left,
I'm gonna-
you're dividing it by
right
two.
this second.
Right.
That's
Here's
the
my
same
guess.
as
It's a stupid guess.
moving the decimal place to the left.
So I got
You're
three
inserting a
confused.
zero.
Don't do such tight
Okay,
increases
so-
either.
Oh, yes,
I
that's right,
started
yeah.
with-
So you
That's the
start with
problem,
a
yeah.
random guess.
So, here it goes.
For x, and then I insert a zero, because that's
Is that
dividing by
dividing
two.
by two? Okay, so.
And then, what's this other operation? You insert a zero, and then you put a one in where there's no.
Okay, wait, say that again. So here,
X over two is insert a zero,
okay,
and then add a half is insert a one where the zero
And
is.
then,
oh,
this is still not, so
okay.
let's all do it one more
Oh,
time.
thank you.
That'll get it for me, because by then I'm, I'm like eight dyadic places into the thing.
Okay, so now I have a homework problem for you. How do you fold sevenths? So what do you have to do to figure out how to
Oh, I
fold
can
sevenths?
do that.
Find the decimal expansion base 2 of 1/7, and that will encode the instructions for left and right folds to fold sevenths. Now it's completely redundant. How do you fold 11ths? What's nice about this is that testing yourself is built in. Right? You're going to get an answer, and you can do the sequence of folds, and if it doesn't give you sevenths, you'll know very quickly.
That's what I was thinking, you can do it on a big piece of paper, a big piece of graph paper, and you can count.
Yeah?
You can see, you can go to yourself.
Here's your fifths. Okay, now, I know I have run out of time, and we haven't even gotten to page 2.
Oh, no.
You still have 15 minutes.
Oh, I still have 50 minutes. Excellent.
15.
Yeah, I have trouble with place value.
What race are we talking
And order doesn't matter.
You know, I saw a website recently that if you give it your age, it'll give you the base that you can report your age in, so you're never older than 39.
Yeah.
And I thought, okay, that's funny, but we should be able to do that ourselves.
Especially 39.
I used to tell people rounded to the nearest century that I was zero. But I
That's not
stopped.
true anymore.
I stopped.
And you did. Let me guess why. Because you're one. Okay, so I'm going to ask you to shift gears, but you have your homework problem. Fold sevenths, fold 11ths, and check yourself. But now I want you to do something completely different. I'm going to take an operation, 1 plus 1 over x. and I'm going to iterate this operation. So what we were just doing was iteration. That means repeating the same recipe over and over. Here is my recipe. X represents an input. So I'm going to take the reciprocal of my input and add 1 to it. Suppose I start with 1. What will be my next output?
2.
2. Now I'm going to repeat with 2 as my input. What will be my next output? 1 plus a half. Can you change that to a fraction for me? Base 10. 3 over 2. And I'm going to turn 3 over 2 into my input. So I take the reciprocal and I add 1. Reciprocal of 3 over 2. 2/3, add 1. 5/3. Repeat.
8/5. 13/8. 21 over 13.
You guys are fast.
Fibonacci.
You're fast. And what do you see? Right, I mean, I'm hearing it all around.
Stuff.
We have the Fibonacci numbers on the top and on the bottom. This is giving us at every step a quotient of Fibonacci numbers. A Fibonacci number over its predecessor. So what's the next one going to be? 34 over 21. 55 over 34, da 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 da. Guess what? That converges.
To feed. 1.6.
Stand up. It converges to phi, which I think is approximately equal to 1.618. Okay. So how would we tell what this converges to? Well, suppose the process stopped. Obviously, it's not going to stop. I'm getting a different rational number at every stage. But suppose we had an input that gave us the same output. X equals 1 plus 1 over x. So I can solve that. Multiply both sides by x. I have x squared equals x plus 1. I can use the quadratic formula. No. Or I could complete the square. X squared minus x equals 1. Leave a space. What goes in the space to make a perfect square? 1/4. A half squared. I add a fourth to both sides, and I end up with the square of x plus a half equals 5/4. So x plus a half is plus or minus root 5 over 2, and x equals minus 1 plus or minus root 5 over 2. I think I have to rule out the negative solution, which I will do just by erasing it.
Why?
Why should I rule out the negative solution?
All the numbers in that sequence are positive.
All the numbers in the sequence are positive. So it's true, the negative solution is a solution of this algebraic equation, but it can't be the limit of that sequence.
Okay, thank you.
Okay, now, which happens all the time, right? We take a problem, we generate an equation, the equation might have solutions that don't come from our problem. I would like to analyze this graphically. So, can we graph y equals 1 plus 1 over x?
I have a quick question.
Yes.
I think I'm a little behind you because I was writing some down to start the first part. But you have x squared minus x plus 1/4.
Yes.
And then in parentheses in the next line should be x minus 1/2 in parentheses squared.
Yes. Yes.
And that goes there.
Yes. And that becomes a plus 1.
Yeah.
Right.
There we go.
Yes. Thank you. Okay, so now back to this question, can we graph this? So what does y equals just 1 over x look like? It has two pieces. And what happens when you add 1 to it?
Moves it up.
Moves it up. I'm increasing every y value by 1. So I'm going to move this up 1 unit. and my other piece will be over here. And then when I find the intersection with y equals x, well, let me just draw the line y equals x. There it is. I have these two intersections. Now, the real reason, though, that I want to draw this picture is because I am iterating this function. Now, what does that mean? It means I take the output and turn it into an input. On the graph, well, let's see. Let me start with 1. Here is x equals 1. I apply the function graphically by going up to the graph. And now this y value is my output. And that's 2. It's not a bad picture. It's not a perfect picture. So that's 2. This is 1. This is 2. How do I turn 2 into an input? I would like to find where 2 is on the x-axis. Yeah, I have y equals x drawn here. So I could just go over to the line y equals x, and now this is the x value 2. Now how do I find the output for the x value 2? I go up to the curve. And there is my x value for 2. What was that? 3/2. And now I would like to turn this y value into an x value. Okay, again, I could reflect across the line y equals x, or I could just go over to the line y equals x, and that will be my x value 3/2. So let me redraw this picture now. I'm starting here with 1. I go up to the curve. I come over to the line y equals x. There's my x value representing my output. I come down to the curve. I want to turn that into, I'm now thinking of a y value. How do I turn that into an x value? Come over to the line y equals x.
Yay.
Generate the output by coming up to the curve. How do I turn that y value into an x value? It's the same conversation again and again. Over to the line y equals x. Down to the curve. Over to the line y equals x. Up to the curve. And what is happening? If you look on page 2, you will see a picture of what's going on here. And this gets attracted to that intersection point so quickly, you can't even appreciate it. You know, when you draw the picture well, it's there. You can't see the cobweb going in. This is called graphical analysis. And we're about to do an example of convergence with strips of paper. How many of you have strips of paper left?
I have some if everybody needs any. You drew that line y equals x because you were saying that you wanted output to equal input?
Yes. But then it was good to have it there because y equals x is the perfect, well, actually I drew it initially because I wanted to know where does y equals x intersect 1 plus 1 over x? Because that would be the point where this operation does not change, becomes stationary. What's cool is that it kind of doesn't matter where you start. You're going to be attracted to this point. But wait, we learned something actually better. Is it obvious from this sequence of numbers that at one stage you're higher than the point, the next stage you're below it,
Oh, yeah.
the next stage you're above it, then below it, above, below. If you do this with a calculator, you will notice that this is below the convergence. This is above. This is below. This is above.
You're shaving off error.
And you're shaving off error every time, but you're bouncing back and forth, which is kind of cool. That's not obvious from here, but now it is obvious from this picture. Okay, grab a strip, because I don't know how much time I have left.
So what you're saying is eventually you're converging on the solution.
Eventually you're converging on that solution.
Okay.
So here's what I would like you to do now. There's a picture on page 2. Ignore the one with the angles marked, and just look at the first picture. Near the end of your strip, make a crease.
On the left, that left.
You know, just actually, what I'm going to try to get you to do is fold a 60-degree angle. So make a crease close to 60 degrees. You can eyeball it. The point again is, though, it doesn't matter how bad you are at making that initial guess. Now, here's the tricky part to describe. Take the top edge and fold it down so it goes along your crease.
In the very corner?
Yeah.
How much like this?
The top edge, no, open up, show me your crease.
Right here.
Okay, leave it creased.
Oh.
So fold the
Then
top
this.
edge, no, fold the top edge so that it actually comes down.
Oh, the
on
other,
the
okay.
crease. Let's see your initial crease. Here's your initial crease. So I want you to fold the top edge so that it comes
Fold away from the.
down along the
Way,
crease.
yeah.
Okay.
Did you do it? I think so. So here's your crease. Fold like this, and you fold opposite. Hold on.
Okay, and then here's what I would advise you to do. Turn the crease over so your bottom edge is your top edge, and repeat that. Fold your top edge so it lines up with your crease. So, in fact, don't open it out. So there's your crease. So fold that down. There's your new crease. Fold that down. There's your new crease. Oops. Okay, so where's your initial crease? Okay. So now, fold, so the top edge goes along the crease.
I know how I would have.
And there's your new crease. Fold so the bottom edge goes along that crease. Now you have a new crease. So the top edge comes along that crease. So
Yeah. So first we fold the
now,
crease.
I have found this is tricky to describe, so help each other out here. You've got, and keep going all the way along, but it looks like,
Seemed like it was kind
yeah,
of perfect already.
kind of perfect.
And,
You can
mine's
say
like
it.
45 degree angle, so it should.
I'm already perfect.
You know, Ted, one thing that I show kids with binary
Yeah.
numbers is you can count on your fingers. Have you seen
Yes,
this before?
up to 1,000.
Yeah. Or, you know,
Show me.
oh, so if you use these as your digits, like going right to left, so it'll be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16.
I
You're
can't
very
do that.
fast.
Every time you hit a power of 2, you have one finger up. Because it's
Okay.
like it's 1,
Yep,
2,
yep,
4,
yep.
8,
Okay.
16,
You're doing it
32.
right.
And then you can go up to 1,000 with 10 fingers.
Cool.
Okay, are you getting it?
Okay, no.
13's a six.
Okay, so,
All right, so
I-
here was
so
my
just-
first crease and my
you know,
first
you're
fold
saying-
and my first down.
and then,
Here,
fold it.
it
So
just
I'm
seemed like
writing
the
about that
8,
little tail.
like there was like a,
That works.
Okay.
I don't know, I mean, it's just like completely vague, but it
So
just seemed like
what I
there was
keep doing
one
is turning it over
easiest way
so
to
my
write
bottom
a
comes
second
my
number.
top.
I
1,
see.
2, 3.
Oh, yeah,
So
this
what
is to make it as close to
Yes.
triangular as
Right.
possible.
And
But
then.
with
No,
8,
no, no,
it's
you're always
Well,
folding,
I'm
you're
writing
always
down.
folding the top or
Exactly,
bottom
right,
edge.
no, I agree,
So
they're
it's-
both, in other
There's your
words, there's,
crease.
there's,
Yes, so fold it so
there's
the edge
numbers
lines
where
up
there's
with that
numbers that
crease.
tie for
My
being
last
most
crease.
Here's your
triangular.
last crease.
I'm sure that that's
Fold it so
the idea. And
edge
so
lines up
for
with that
13,
crease.
1, 3, 4, 5, which is 2,
Here's
2,
your
4,
last
5.
crease.
Mm-hmm, and they both are like
So the
equal,
edge
yeah,
lines up
right, and I
with
think,
that
and I
crease.
think you can probably
And so on.
maybe measure their size using like that Conway chart.
Oops.
You know, with one halves and maybe their size. is
Okay,
the
so
same.
are we,
I'm a little lost.
are we able to get a strip that looks like you're
So we're
coming in
eventually
on?
gonna get it equal on
Maybe something that kind of look like these.
So are you working on coming up with an algorithm to figure out which ones are separate and which ones are
Not,
I don't know
not,
what we're
not yet, really, I've just been enjoying the pictures.
To line up with that crease. Now,
Yeah,
here's my latest
yeah, I
crease.
just haven't had time to concentrate on it. But no, I agree, that's the way to think about it, or at least that's the way to start. I just, my computer was broken, so I had to.
Oh, they started a different way, she was doing something else.
Despite of that, that's not
Yeah, because it's a work computer and dot,
wanna have
They
this.
were trying to fix it and it completely died, so then they just replaced it.
Okay, Brandy is giving me the hook
They're
here.
on a 4-year replacement cycle.
So-
Another
I am, of course, leaving you with this handout, but let me just, I would ordinarily not do this. What's going on with this handout? We're again repeating an operation. Let me just end by figuring out with you what is the operation we are repeating. So here is my strip of paper. By the way, this doesn't work if the strips of paper don't have parallel edges. Here is, let's say, my initial angle, x. So because these are parallel strips of paper, this is also parallel edges, that's also x. So what's this angle?
180 minus x.
180 minus x. And then when I make this crease, what is my new output?
180 x over minus x over 2.
Half of this, which is 90 minus x over 2. Now if you do that, suppose I started with a perfect guess of 60. What's 60 over 2?
30.
And 90 minus 30?
60.
So if I start at 60, I stay at 60. What's very cool about this is if you're way off from 60, you quickly converge to 60. Now, let me just repeat this picture, which, by the way, is also...
Hey, how appropriate. Boy, the joy.
Randy is really giving me the hook here.
Okay.
Fibonacci sequence!
All right, so what's the deal here? My output I get by doing 90 minus x over 2. Let's quickly draw a picture. How do I graph 90 minus x over 2? Y equals 90 minus x over 2.
Take that, flip it, move it up 90.
It's a line with slope, blank, y-intercept, blank, slope negative a half,
And it's going through 90.
y-intercept 90. Now I want to do this business of turning output into input again. So I'll draw the line y equals x.
1.5.
And we just figured out if I set x equal to 90 minus x over 2, I won't do the algebra, I get x equals 60. But now what happens? I pick any guess I like. Terrible, terrible guess. 90 degrees. I go over to, oops,
You start at the x.
90 degrees. I go up to my output. I turn my output into my input. I go up to my output. Turn my output into my input. And what's happening? Just like the 360. And not only that, but it's repeating that behavior again of alternate answers being above and below. But of course you can't tell that on the paper. It gets to 60 so quickly, it just looks like 60. How would you know one's bigger and one's less? Okay, I think I got the hook, and
Y equals x still?
this is y equals x.
For his
Because
reflection.
you lose y, you use y equals x to turn output into input. You can either think of it as reflecting across the line,
Okay.
or this cobweb thing going over to the line, you're at y equals x, so now the x value is the y value, and your output is your input.
Thank you.
So that's perfect, because I love to ask a question and not answer it. That one is not answered. But I'll tell you,
Why?
it's not a perfect equal answer. Thank you.